This is lesson 5.4, and we're going to talk about e to the x, we're going to talk about its derivative, and we're going to talk about its integral, both in this section. So let's first of all start out by talking a little bit about what is e. E itself is described as the limit as x approaches infinity of the equation 1 plus 1 over x to the x power. And if you graph this, what happens is it approaches a value that is about 2.71828 ... and that value is called e. And sometimes they call it Euler's number because the E was for Euler, or sometimes they call it, I believe, Napier's number. So e itself is just a constant, but e to the x is a function. And e to the x is a function that looks like this black curve here. And the most important point right there is that it goes through 0, 1. And that's really important to remember, and probably pretty obvious, because if you took e to the 0 power, you would get 1. Now you might remember, or you might not remember, that e to the x is the inverse of ln x. Ln x is the green curve. So one thing that's kind of important to notice, when you look at the e to the x curve, notice that it passes through 0, 1, and it's going up towards infinity. And if you followed it to the left, it's going to level out. It's never going to cross the x-axis. So e to the x is always above the y-axis, which means it's always positive. Ln x, on the other hand, is always to the right of the y-axis. So if you recall, when we took natural log, you can't take the natural log of a negative number. So notice that it never goes to the left of y, which means you never have a negative x. This one is approaching infinity very slowly as it goes to the right, and it approaches negative infinity as it goes this way. Okay, so a couple things. Since natural log and e to the x are inverses of one another, if you take the natural log of e to the x, you get x. And if you take e to the ln x power, you also get x. And that's because they're inverses. That's what happens when you have inverses. Okay, so the derivative of e to the x is itself. The derivative of e to the x is e to the x. The derivative of e to the u, recall that u means that it could be x squared or x cubed or cosine or tangent or any function. So if you take e to the u, then you multiply by its derivative, e to the u du. So for example, if I want to take the derivative of e to the 3x, then first of all I rewrite e to the 3x, that's the first part of the derivative, times the derivative of 3x, which is 3. So the derivative of e to the 3x is 3e to the 3x power. Alright, let's look at another example. If I have e to the 2x minus 1, first of all, you write e to the 2x minus 1 times the derivative of 2x minus 1, which is 2. And so e to the 2x minus 1, the derivative is 2e to the 2x minus 1 power. Pretty simple. If I have e to the negative 3 over x, first of all, you might even want to rewrite it as the derivative of e to the negative 3x to the negative 1, just so that you have a full idea of what's going to go on here. So the derivative here is e negative 3x to the negative 1 power times the derivative of this negative 3x to the negative 1 power. Remember, we're talking derivatives, so when you bring the negative 1 to the front, it becomes positive 3x to the negative 2 power. So if you write this all together, you're going to have 3e to the negative 3 over x divided by x squared. Alright, that's the derivative. It's just itself times the derivative of the power. Now we're going to do some integration. So if the derivative of e to the x is e to the x, then what's the integral of e to the x? Well, you probably figured it out. It's e to the x. So e to the u's derivative, integral, when you integrate e to the u, you also get e to the u, and in both cases we put plus c. Now the difference between this is that when this is e to the x, it's just dx. But when this is e to the u, you have to check and make sure that your du is complete. And so the du has to be the derivative of whatever that function is right there. So let's look at some examples. If I have e to the 3x plus 1, then this would be my u. And so if u were 3x plus 1, the derivative of u would just be 3 dx. So in this problem we need a 3 here, which we can balance with a 1/3. And you can actually go ahead and rewrite it if you're more comfortable with that. 3x plus 1 is u. 3 dx is du. Integrating this, e to the u becomes itself when you integrate it. And then we're just going to make a little substitution here that we know u was 3x plus 1. And plus c, and there's your integration. Okay. Sometimes you might want to rewrite the problem, like I did with other integrals that we've done here recently. Like maybe rewriting it as e to the negative x squared, and then putting the 5x after that, and then the dx. And if you're not sure what should be u, keep in mind that when we integrate it, we called this part u. So we will always let the exponent be our u. The derivative of that would be negative 2x dx. So if you look at this problem, we have a 5 here that we don't need, so I'm going to bring the 5 out. And then we need to put a negative 2 in to go, let's go right in here. We need a negative 2 to be right in there. So it would be negative 2x dx. So we're going to divide by negative 2 to balance the fact that we put a negative 2 in the problem. So if you were to rewrite this, I would have negative 5 over 2 integral e to the u, and then all of this will become my du. Negative 5 halves, e to the u becomes e to the u when you integrate it, plus c. So negative 5 halves e to the negative x squared plus c. I think it's easier to use the u when you're dealing with e, but if you can recognize it and you don't need the u and you don't have to do the substitution, that's all right also. Alright, for this problem especially, well, let's rewrite it. So we have e to the 1 over x power times 1 over x squared dx. I just took the 1 that would be the coefficient for e and took this whole part and just moved it to the side. So if you look for your u is going to be the exponent, so that's 1 over x. Remember 1 over x is the same thing as x to the negative 1 power. So du would be negative x to the negative 2 power, which would be negative 1 over x squared dx. And we have the 1 over x squared. We're just missing the negative 1. So we'll put a negative inside and outside. So I'm going to have negative integral e to the u du. So integrate e to the u and you get itself. And then negative e to the 1 over x plus c. Okay. How about some trig? If we rewrite this problem, we could write it as e to the cosine x times sine x dx. And you might recognize immediately, well, sine, oops, I forgot my x. Sine x dx is the derivative of cosine x. Or you could double check for yourself and say if u is cosine x, what is the derivative of cosine x? So we're pretty close. The derivative of cosine is negative sine x dx. So what are we missing? We're missing a negative here. So we put a negative on the outside. So negative integral e to the u du becomes negative e to the u plus c. Now u is cosine x, so we're going to make that substitution back in there. And my answer is negative e to the cosine x power plus c. Alright, let's look at one more. This problem doesn't match the other problems for a couple of reasons. The first one is my exponent here is just x. So if I have e to the x, its derivative, the derivative of the x would just be the dx, and that would be complete, and we have this 1 plus e to the x that we're not sure what to do with. So that's one reason we have a problem that's different. The other reason that's really important is that this is a fraction, and even if we rewrite it, it doesn't seem to really do anything for us. So let's see. If I rewrote this as e to the x times 1 plus e to the x to the negative 1 power dx, then that's not doing a whole lot for us. Other than it made it into a product, and we know there's no product rule for integration, so we would still have to try to do some form of u. So I'm going to go ahead and mark this back out, because when you see a fraction, one of the things that you want to test anytime you come across a fraction where it's not immediately obvious to you what might be happening, the fraction is what tells me, let's try the denominator as my u and see if this turns out to be in the format of du over u, which from the last section we did with 5.1 and 5.2, if it's in the format of du over u, then it integrates to become a natural log. So let's look at this. If u is 1 plus e to the x, du would be 0 plus e to the x dx. Okay, so this bottom part would be my u, and this top part with the dx would be du. And we're integrating. Now I'm leaving off the 0 and the 1 for now because I've switched it to u's. When I switch it back to x's, then we'll put the 0 and the 1 back into there. So if I have the format of du over u, this automatically integrates to become the natural log of u plus c. So this problem has e to the x in it, but it's not an e to the x integral. Now I'm going to change the u back into 1 plus e to the x. And I don't need the plus c because we have limits of integration. So we'll do 0 on the bottom and 1 on the top. So let's plug this in. This would be ln of 1 plus e to the first minus ln of 1 plus e to the 0. So that is ln of 1 plus e, which 1 and e are both positive numbers, so I can change that to parentheses, minus e to the 0 is 1, so this is minus ln 2. You can put this in your calculator and you can get a decimal for it, or if you want to, which I usually do, I just leave it in terms of ln. Since this is subtraction between two natural logs, I can put this as 1 plus e over 2. So my answer is ln of 1 plus e over 2. And that is it. So I'll have some practice problems for you tomorrow in class, and be sure to review this video if you have questions.